Hi, everybody, welcome to first international web conference on forecasting. I am Ozan Kocadagli from Department of Statistics, Mimar Sinan Fine Arts University. Today, I will talk about Bayesian learning-based Gaussian approximation for artificial neural networks. This presentation organized as follows. First, I will talk about literature survey, structure of neural networks, Bayesian learning, Gaussian approximation, fixed hyperparameters approach, and lastly, benchmark dataset application with gradient-based algorithms. In the literature, there are many remarkable studies. For example, McKay proposed Gaussian approximation, and then Neil looked at advanced Bayesian simulation methods, specifically hybrid Monte Carlo. The other good sources, Insha and Muller, Freitas, Chuan Go, Vantalato and Vahtari, Malvala, Mirkitani, Gutrich, Scower, Beam, and Kocadagli. In the study, we handled feed-forward neural networks. This framework includes inputs, hidden layers, and outputs. In order to estimate network parameters, researchers intend to minimize mean-squared error. Unfortunately, this approach causes two types of errors: estimation and approximation. The approximation error arises because the exact nonlinear behavior of the regression function is seldom known. Consequently, true function has to be approximated by a combination of parameterized Bayes functions. The estimation error is the result of our lack of knowledge about the conditional distribution. Likelihood methods do not attempt to estimate this distribution, but instead minimize the empirical risk. To summarize, the approximation error is inversely related to number of model parameters, while the estimation error is directly related to number of parameters. This trade-off is well-known bias-variance trade-off. The only ways to reduce bias and variance error terms simultaneously are to either increase number of data or to model the noise characteristics and incorporate priori knowledge about the form of the estimator. One way, perhaps the simplest, of making use of prior knowledge is to impose smoothness constraints on the model. The scheme is known as a regularization. It reduces the infinite number of possible solutions to learning problem to one that balances bias, variance, error terms. The other approaches for controlling the complexity, respectively, are stopping, training with noise, mixes of networks, growing and training techniques. As mentioned before, complexity directly related to estimation and approximation errors. According to Occam's razor rule, analysts prefer simple models against complex ones. Actually, Occam's razor rule is embodied automatically and quantitatively in Bayesian methods without penalty function. In the Bayesian learning, the prior distributions are defined parameters. This expresses our initial beliefs about their values before any data has arrived. When data is observed, this prior distribution updated the posterior one. Generally, Bayesian treatments of learning in the artificial neural networks are typically based on Gaussian approximation, ensemble learning, and Markov chain Monte Carlo methods. According to Gaussian approximation for Bayesian learning, the uncertainty in the parameter space is assigned a probability distribution representing the degree of belief in different values of parameter vector. By maximizing the posterior distribution over the parameters, the most probable ones can be determined. The probability of data value given the parameter vector can be constituted in equation first. Provided data points are drawn independently from equation first, so the likelihood can be constituted for an observation as follows, given in equation 2. The probability distribution of parameters should reflect any prior knowledge about network mapping that is expected to find. Generally, distribution of parameter is assumed as an exponential form, as given equation 5. When a prior distribution and an expression for the likelihood are chosen in order to find posterior distribution, Bayes' theorem can be used in the equation 8. Thus, H theta can be written in the form given equation 9. In order to maximize posterior distribution, H theta can be minimized. There are two hyperparameters in the equation 9, like a beta and alpha. While beta controls noise, alpha deals with complexity. Using the rules of probability, the distribution of outputs for a given new input vector is given by equation 10. In the context of Bayesian learning, there are functions called like a energy function. In order to minimize these functions, gradient-based algorithms like a gradient descent with adapted learning, BFGS, and Lemech-McQuart can be used. Alternatively, Monte Carlo simulation applied to estimate artificial neural networks as well. For instance, Metaple's Hastings very efficient algorithms to handle it. In the application section, in order to compare the performance of Bayesian and traditional artificial neural networks, a benchmark data set with two inputs and one target that was considered as follow figures. To train the traditional artificial neural networks, the gradient descent, as known also the steepest descent, and gradient descent with momentum methods were handled. For Gaussian approximation with fixed hyperparameters of Bayesian neural networks, Kocadagli, well-known BFGS algorithm was preferred due to its advantage in the evaluation of Hessian metrics. Results are summarized in the next slides. In the slide, two tables belongs to performance of artificial neural networks trained by gradient descent and gradient descent with momentum. According to analysis results, the best performances given in the rows with bold characters. Artificial neural networks trained by different neurons and considering different tuning parameters. In the slide, the first table shows the results of Gaussian approach with fixed hyperparameters, in which Bayesian neural networks trained by BFGS. In this table, the row with bold characters give the best results of analysis. In the next table, the comparison of the best models is given with respect to training of mean square error, test mean square error, training correlation, and test correlation. According to this table, apparently Gaussian approach gives better performance than traditional artificial neural networks, because Gaussian approach balance noise and complexity, considering alpha and beta hyperparameters. As seen in these figures, if we get small alpha and beta values, this framework produces little bit smooth hypersurfaces. However, if we get larger beta values, this framework produces more convenient estimation. As a result, it can be said that Bayesian regularization is superior to traditional artificial neural networks trained by gradient-based algorithms. Occam's razor rule actually is embodied quantitatively in the Bayesian approaches without penalty function, since complex model is self-penalizing automatically. The fixed hyperparameters allows the analysts to control the model complexity in addition to searching the high-density regions of parameter space. Gradient-based algorithms provide efficient and robust solutions in the context of training artificial neural networks. Alternatively, the parameters of artificial neural networks can be estimated using Monte Carlo simulation as well. Thanks for your participation.